Hey everyone, and welcome back to The Explainer. If you look around, concrete is literally everywhere. But engineers don't just pour the exact same mix for a simple sidewalk that they do for a massive bridge over the ocean. Today, we're decoding concrete grades to figure out exactly how to choose the right concrete for the job.
Now, I want to kick things off by completely shattering a common misconception. Our source material points out an absolutely crucial fact. It is not entirely true that the strong concrete is always a durable concrete. For a really long time, there was this heavy emphasis just on compressive strength. The thinking was, make it stronger and it will automatically last longer. But modern concrete technology has shown us that this is a dangerous oversimplification. Strength alone simply will not save a structure if the environment is hostile.
Okay, let's dive into this. Here's how we're breaking it down today. First, the durability dilemma. Then, decoding concrete grades, followed by the 5 exposure levels. After that, we'll be matching the grade to the job, and we'll wrap up with the all-important water-cement rule.
All right, part 1, the durability dilemma. So, the very second concrete cures, it is actively fighting a war against its surroundings. It's true. Think about it. You've got vastly different structures out there. On one hand, a massive cooling tower dealing with industrial fumes and wild thermal stress. On the other, an enormous dam holding back millions of gallons of water under immense hydrostatic pressure. A single one-size-fits-all type of concrete? Yeah, no way that survives both of those extremes.
And that brings us to a huge paradigm shift in construction engineering. We absolutely have to look at the environmental exposure, not just the raw compressive strength. Concrete durability is really defined as its ability to resist weathering action, chemical attacks, and abrasion while retaining its original form and quality over its entire lifespan. If you build a jetty pier in marine conditions with a standard strength concrete but completely ignore the harsh saltwater environment, well, you're looking at disastrous consequences.
Moving right along to Section 2, decoding concrete grades. Now, what's really interesting about this is how engineers pack so much precise information into just a tiny little label. Take M20, for example. The M simply stands for mix. And the 20? Well, that means if you pour this concrete into a standard 150 millimeter cube and let it cure for exactly 28 days, it can withstand 20 newtons per square millimeter of compressive force. It's a really smart, highly standardized way to communicate that baseline strength.
And then the Indian Standard Code, IS 456, beautifully categorizes these grades into 3 main buckets. First, we have ordinary concrete, running from M10 to M20, which you'll typically see used for simple, everyday foundations. Then we step it up to standard concrete, M25 to M55. That's the real workhorse of modern reinforced construction. Finally, we've got high-strength concrete, from M60 all the way up to M80, and that stuff is strictly reserved for highly specialized heavy-duty applications.
Okay, Section 3, the 5 exposure levels. Because strength isn't the whole story, we have to account for the environment. The IS 456 code essentially maps out the environment into 5 legally categorized threat levels. It starts at mild, meaning it's protected against the weather. Next up is moderate, sheltered but still exposed to some moisture. Then things get quite a bit tougher with severe, where you have alternate wetting and drying. Very severe brings in seawater, spray, and freezing conditions. And finally, extreme, which involves harsh tidal zones or direct contact with aggressive chemicals. To put that into perspective, consider a transit line braving heavy snow and freezing temperatures. Frost action is literally one of the most powerful weathering forces on the planet. When water inevitably seeps into the tiny pores of the concrete and freezes, it expands. That creates immense internal pressure. Without the right concrete mix, that constant alternate freezing and thawing is going to lead to rapid deterioration and, eventually, complete structural failure.
This brings us to Section 4, matching grade to job. So how do we actually go about choosing the right grade of concrete for these different jobs? Well, the engineering code mandates minimum grades based directly on the hostility of the environment. And this brilliantly illustrates how it scales. If you're pouring reinforced concrete in a mild environment, you're perfectly fine to use M20. But the moment that environment shifts to moderate, you have to step up to M25. If it's severe, you're jumping to M30. The minimum grade steps up precisely as the environmental threat increases.
There's also an absolutely critical difference between plain and reinforced concrete. Plain concrete, which has no metal inside, can survive on much lower baseline grades, like, say, an M15 for moderate exposure. But The very second you embed steel rebar inside, the whole game changes. You suddenly need a strict minimum of M20, even for the absolute mildest exposure. Why? Because the concrete is now acting as a dense protective shield to stop oxygen and moisture from rusting the steel hidden inside.
And finally, Section 5, the water cement rule.
The source material lays this down as an absolute golden rule, and I quote, "The free water cement ratio is an important factor in governing the durability of concrete and should always be the lowest value." Now, I know it is incredibly tempting on a job site to just add a little more water to make the concrete flow easier, but excess water leaves behind microscopic voids when it eventually evaporates. And those voids, they create a porous, weak structure that basically rolls out the red carpet for moisture and chemicals.
So the crucial point here is this strict inverse relationship. For reinforced concrete in mild exposure, your maximum free water to cement ratio sits at 0.55. But if you're building in an extreme environment, that ratio drops aggressively down to 0.40. As the environmental threat goes up, the allowed water must go down. It's the only way to force the creation of a denser, highly impermeable barrier.
0.40. That is the absolute maximum water-to-cement ratio allowed for reinforced concrete facing extreme, aggressive environments, like those tidal zones or heavy chemical plants we talked about. Now, this results in a thick, sticky mix that requires a ton of effort to properly place and compact, but it is entirely, 100% necessary to guarantee that the structure actually survives its intended lifespan.
As we wrap up today's explainer, I want to leave you with a quick thought. The next time you walk down a sidewalk, or look at a bridge crossing a saltwater bay, or even just glance at your own foundation or driveway, ask yourself, based on its specific environment, do you really know if it's truly built to survive? Because as you've seen, the science of concrete goes so much deeper than just pouring gray liquid into a mold. It's a precise, highly calculated battle against the elements. Thank you so much for joining me today. Keep asking those questions, keep looking closely at the structures around you, and I will see you on the next explainer.